This is Facility Science Podcast number 23. I am Jason Doolittle, and today I'm talking about elevators. And mostly I'm talking about the modern automatic passenger or freight elevators we commonly see in commercial and residential buildings, although the basic concepts might apply to any kind of elevator. And if you like this podcast, it would be really helpful to me if you would share it with someone you think might find this type of information useful. Also, if you want to help me keep making the podcast and you like to shop at Amazon.com, you can head over to facilityscience.com/support and click the link to Amazon that's there. Amazon will give me a small referral percentage at no additional cost to you for anything you buy after clicking my link. And there's also a couple of other support options there that might interest you. So there are two basic types of elevators, traction and hydraulic, although in the last few years there have been, development of what we might call a third type, which is an elevator that uses electromagnetic propulsion. And for reference, I'm recording this in late 2019. But other than the details of the mechanisms of vertical movement, which I'll talk about, most elevators have the same basic parts, so I'll talk about the parts first. So the basic idea of an elevator is that we have some kind of a box that people ride in, and that box moves up and down an elevator shaft, which we call a hoistway, to bring people to the different floors of the building. That's basically how it works. And so the first part we'll talk about is the car. It could be called a cab or a carriage, and that's the box part of the elevator that the people ride in. And it's a box with doors on it that moves up and down, and there are some controls inside that allow the riders to choose their floor. You've likely seen and been in elevators of various shapes and sizes made out of different materials. Most cars are rectangular metal boxes, although some are round or other shapes, and some are made out of other materials like glass to give the riders a view of whatever might be outside the elevator. There's usually an access hatch on top of the car, although contrary to what you see in the movies, it's not meant to be open from the inside and is usually locked or latched from the outside. We have the hoistway, or the elevator shaft, and that's the space in which the elevator car moves, right? It's a vertical column of space. And inside the hoistway, or the car, obviously, there's the guide rails on which the car is mounted, and there's various switches, or sensors, and safety devices. So at each floor, there'll be some mechanism to indicate to the elevator controller that the car is approaching the floor, so it should slow down, and also to indicate when the car is level with the floor and should stop. At the top and bottom of the hoistway, there might be some limit switches to tell the controller that the car can't travel any further. We've reached the top or the bottom, and the elevator should be stopped right there. Now, other than the mechanical device which moves the elevator car up or down, so that's the hydraulic piston or the cables, the cab, the car, isn't attached to anything. And if it was, it wouldn't be able to move up and down. Instead, it's captured on guide rails with rollers that keep the car from swinging or swaying from side to side, so that it's always lined up properly in the hoistway. In some elevators, mostly traction elevators, that's the kind where the car hangs from cables, the guide rails also provide a surface for a braking device to prevent a free fall of the elevator cab if the cables were to break. Elevators also have doors, usually two different types of doors. You have the car doors, that's part of the car assembly, and these doors keep the occupants of the elevator from falling out or getting hurt or crushed by things outside the car as the car moves through the hoistway. And then we also have the hoistway doors, and these doors are in the hallway at each landing, and they're to keep people in the hallway from falling into the open elevator shaft or getting crushed or otherwise injured when the car moves past. And generally, automatic elevators are set up with various locking and interlocking mechanisms, so a person inside the car can't open the doors if the car isn't properly lined up with a set of hoistway doors at a landing. And also, the hoistway doors generally can't be opened by normal means if the car isn't lined up properly at that particular landing, again, in order to prevent someone from opening the doors and falling in. At the very bottom of the hoistway, we have what is called the pit. And this is some sort of extra vertical space below the bottom landing where the elevator will never generally travel under normal circumstances. And the pit provides space for various elevator components, including parts that might be hanging from or attached to the bottom of the car. And there are a few specific things you might find in an elevator pit. There is a safety device, maybe a last resort safety device in the pit called a buffer. And the buffer is some type of spring mechanism designed to catch the car if it were to fall into the pit. And the buffer mechanism would be designed or selected based on the energy expected from a falling car, which would be, based on the expected weight and maximum speed of the car as it fell into the pit. And the idea is that the buffer will prevent people in the car from being killed by the impact, although my understanding is that they might be injured. Also in the pit, you would find the hydraulic piston and hoses or piping or whatever for a hydraulic elevator. You might also find other machinery or machine components depending on the exact elevator design. And then unfortunately, you might also find water in the pit, and that's generally a bad thing and should be fixed as soon as possible. All right, now we can move on to the elevator machine room, and the machine room provides space for the machinery that actually moves the elevator. And you'll also typically find the elevator controller in the machine room. For a hydraulic elevator, the machine room contains the hydraulic power unit. This is a thing that consists of a tank of hydraulic fluid, hydraulic oil, with a pump to pump oil into the piston that raises and lowers the elevator. The machine room for a hydraulic elevator has to be located close enough to the elevator pit to effectively pump oil into the piston, and that's basically the main restriction on where you have to locate it. And typically you'll find the machine room for a hydraulic elevator near the elevator at the lowest floor. For a traction elevator, the machine room contains the traction machine. It's a motor and a sheave that moves the cables in order to move the car, and I'll talk about that a little more in a minute. The machine room for a traction elevator is going to be directly above the hoistway because the cables have to go across the sheave in order to move the elevator, so it's going to be right above. Some elevator systems don't have a machine room at all and instead include everything inside the elevator shaft, inside the hoistway. We call these machine roomless elevators. Generally, these designs put the hydraulic power unit, the pump and oil reservoir, in the pit under the elevator car, or they put the traction machine at the top of the hoistway, so inside the hoistway, but at the very top. Although I've seen at least one traction type design with the traction machine in the pit under the cab. And this machine roomless concept is enabled by advances in miniaturization of motors, and is generally done for space-saving purposes. If you contain everything required to run that elevator inside the hoistway, you don't have to make extra space for a machine room outside the hoistway. All right, now elevators have various controls and indicators. We have controls inside the car that allow riders to select the floor they want to travel to, also to close the door or to hold it open, and to signal for help in the case of entrapment or emergency. We also have various key switches to allow service personnel or firefighters to put the elevator into special operating modes. The control panel inside the car is called the car operating panel, often shortened to COP. And then we also have indicators inside the elevator to tell the riders which floor they're on and which direction they're traveling in. In the hallway, we have controls to call the elevator and indicators that tell us where the elevator is and which direction it's moving in. And for groups of elevators, we might also have an indication of which elevator will be servicing our call. And it's also common to find a firefighter's key switch at a hall station, which allows a firefighter with the proper key to take control of an elevator in case of an emergency. And then there's usually a control panel on top of the car to allow a service technician to operate the car from up there. And generally, this panel, the one on top of the car, can be used to completely lock out all the other controls of the elevator, since being on top of the car is the most dangerous place to be. The system's usually set up so if an elevator technician is operating the elevator from the car top control panel, no one else will be able to do anything with any of the other controls. And then another important component is the elevator controller, and this is the device that receives input from all the various controls and sensors and uses that information to decide how to move and start and stop the elevator and which calls to service and in which order. And the controller logic will also decide which car to dispatch in a group elevator system. And modern elevator controllers are electronic and computerized and programmable. You also can find older controllers that might use relay logic or something more primitive than electronics, which is kind of interesting, but also much more complex, at least for the maintenance technician, and less flexible. And they also take up way more space. Okay, now we can talk a little more about the different types of elevators. I said there's two types, traction and hydraulic. So a traction elevator is the type of elevator that's hoisted from above by cables, and cables are often called ropes in the elevator industry. The traction machine, which is the device that moves the elevator, it's made up of a motor and a sheave, is at or above the top of the hoistway. And traction elevators have a counterweight, or possibly multiple counterweights depending on shaft geometry, that balances the weight of the car. And the counterweight has a weight equal to the car plus some percentage of the elevator's capacity. The cables, the ropes, are attached to the car, and they go up to the top where the motors are. They pass over a sheave, and a sheave, I keep using the word, but a sheave is a wheel with a channel around its perimeter for the cable to lay in. So if you think of a pulley, that's the thing you might pass a rope through to change the pulling direction of the rope. The wheel inside the pulley that the rope passes over, that spins in there when you pull the rope, that's a sheave. So the cables pass over the sheave, then they go back down the shaft to attach to the counterweight. Basically, you can think of a long cable with the car at one end and the counterweight at the other end, and then that whole cable assembly is just slung over the sheave at the top of the hoistway. And so the motor turns the sheave, and that puts more cable on one side or the other to raise or lower the car. For safety reasons, there are multiple redundant cables in this type of elevator. Generally, the car will still be carried safely even if most of the cables were to break. They're designed so that there's redundancy in the cables. Now, the counterweight and the car with passengers in it approximately balance each other on average. The motor turns the sheaves to let the car or the counterweight fall in a controlled way, which would then bring the other one up. Of course, the counterweight in the car will rarely, if ever, exactly balance, right? Because the weight of the passengers will vary widely. They're never going to be exactly the same. And the difference between the two weights is made up by the friction between the cables and the sheave. If there were no friction at all, the heavier piece would just free fall to the bottom and stay there. And the fact that this type of elevator relies on this friction is why it's called a traction elevator. The system uses traction or friction of the sheave wheel on the cables to move the elevator and to hold it in place when we don't want it to move. This counterweight mechanism allows a traction elevator to be fairly energy efficient, right? The motors, they only have to move a weight that is the difference between the car and the counterweight rather than having to hoist the whole weight of the car and the passengers. We only have to use the motor to make up the difference, and gravity does the rest. And some more modern traction elevators do even better by building generators into the system. Whenever the heavier half of the system is moving down, right, it's basically falling down in a controlled way. It doesn't require any power. All you have to do is sort of let the sheave turn, and the heavier side will just fall on its own. The elevator can use the energy from that controlled fall to turn a generator and generate electricity. It's similar to the concept of regenerative braking in electric cars, if you've ever heard of that. Generally, the elevator is hoisted with some number of steel cables, and the traction machine, that's that motor assembly with the sheave and the friction and all that, is generally at the top of the hoistway, but there are many possibilities. And some elevators use steel belts instead of cables, and the belts are said to be more efficient for various reasons, or even a combination of belts and cables. And sometimes the traction machine is at the bottom of the hoistway in the pit rather than at the top, and I think that's generally for smaller elevators. Traction elevators can be built to travel several hundred meters vertically. I'm not sure exactly what the limit is. I think I've seen 500 meters given as a limit somewhere. And browsing around, the highest elevator I was able to easily find advertised for sale was, I think, 300 meters, something like that. And the limit has at least partially to do with how long we can feasibly make steel cables. Although some, advances in material science and technology might allow us to make suitable cables out of carbon fiber, things like that, various types of fibers, which would help deal with the sort of physical limits on steel cables. And for very tall elevators, we actually have to start to deal with the weight of the ropes, the cables, Steel cables are very heavy, right? And longer cables obviously weigh more. So when in a very tall elevator, most of the rope is on one side or the other. Say if the car's at the very top or the very bottom, you have a lot of rope on one side. The entire system can become unbalanced and potentially overcome the traction mechanism, or at least make the amount of traction we need not feasible to provide. And this problem has a solution called rope compensation. And for this, we hang an extra set of ropes from the bottom of the car, and these ropes pass through a sheave in the pit. And this sheave is passive, by which I mean it isn't turned by a motor. It just acts to guide the ropes and allow them to change direction. The compensation ropes then they pass through that sheave and they go back up to attach to the bottom of the counterweight, basically mirroring the arrangement of the hoisting ropes. The compensation ropes move back and forth as the car and counterweight move, so that there is always the same amount of rope on either side of the traction machine, some amount of the hoisting ropes and some amount of the compensation ropes. So on both sides, there's the same amount of rope. In this way, the weight of the ropes is removed from the traction balancing equation. It's not an issue anymore. Of course, the structures and the ropes themselves still have to be able to support all that weight, which is another issue. Okay, now we can move on to hydraulic elevators. And a hydraulic elevator is pushed up by a hydraulic piston from below. And this is a very simple machine. It's very low complexity, easier installation than a traction elevator, and also easier maintenance relative to a traction elevator. Hydraulic elevators tend to be less energy efficient than traction elevators because the hydraulic pump has to move the entire weight of the car plus the passengers against gravity. Because I said before that the traction gains considerable efficiency due to the counterweight system. The hydraulic piston would be in the pit underneath the car, and sometimes the piston is actually in a hole under the pit if it's long and needs extra space, underneath. And sometimes it's fully contained in the pit. And depending on the height of the building, there can be just one piston, or there could be multiple pistons that operate in stages. And a hydraulic elevator is limited to 8 or so floors. After that, the hydraulic piston system gets too big or too complex to be reasonable, and then we start using a traction elevator instead. And I said there was a sort of a third emerging type, which is a type of elevator that uses magnetic propulsion. This is a fairly new concept that uses electromagnets and the hoistway to move the car up and down. And since this doesn't require any ropes or pistons, there's effectively no limit to how high an elevator that uses this kind of magnetic propulsion could go. And they can also conceivably move sideways or horizontally. I'm fairly certain these exist in the wild, in the real world, but I don't think they're widely used yet. And this is, again, I'm recording this in late 2019. So the electromagnetic propulsion elevator, that's sort of the third bonus type. And so while I said there were two basic types, the hydraulic and the traction, there are many different elevator designs, some of which would even combine elements of the hydraulic and traction concepts. And I imagine in the future, if the magnetic propulsion idea takes hold, we'll get some hybrids of magnetic and traction and hydraulic and whatever makes the most sense in a given situation. And this is getting a little bit longer than I want it to be, and I have a lot more elevator notes, so I think I'll cover one more sort of subtopic here and then leave the rest for a part 2. And the last sort of topic I want to cover here is, if you're responsible for an elevator, there are a few things you should do. Okay, you should make sure that the elevator is properly inspected and certified by qualified professionals based on the appropriate standards and at the appropriate time interval. It's usually annually, but twice a year in some places. You should definitely at all times have the phone number of a reliable and qualified elevator service company in case somebody gets trapped in your elevator and you need help getting them out. You should have a set of all the keys necessary to access and service your elevator, including the appropriate hoistway door release tool, the tool you'd use to open the hoistway doors even if the car isn't there lined up. That's a drop key or whatever else applies to your elevator. And these should only be used by the trained service personnel. And while most elevator service technicians and properly trained firefighters can probably get into your elevator without your help if there's an emergency and they need to do it, it will be easier and safer both for them and for the people in the elevator, and faster, and also less likely to damage your elevator if you can provide quick access to the keys. So you don't necessarily need to use the keys, carry them around in your pocket, but You should have them available in case somebody needs to get access to the elevator. You should also not allow anybody without the proper training to work on the elevator or access the hoistway or pit. So modern elevators are very safe if used properly. I'll get into some of the safety mechanisms in part 2, but people that don't know what they're doing can hurt themselves and also potentially cause damage or misconfiguration to elevator components, making the elevator less safe for the passengers. And then also what you should do is you should call for help if somebody gets trapped in your elevator. Rescuing people trapped in an elevator can be a very dangerous operation, again, both for the rescuers and the people being rescued. So in general, you want only trained personnel to attempt the rescue. In a non-emergency situation, you'll want to call your favorite elevator technician. And in an emergency situation, you'll also want to call your local fire department in addition to the elevator technician. And again, I'll go into some more detail in part 2. So I'm going to leave that here for now. You can find my notes for this topic at facilityscience.com. If you have any questions or comments about this topic or suggestions for other topics that you would like to hear about, you can reach me by email at podcast@facilityscience.com or at facilityscience on Twitter. If you like this podcast and want to help me keep making it, head over to facilityscience.com/support and see if any of the support options there appeal to you. I hope this is helpful to you, and thanks for listening.